Today we have lecture 10-2 on passive filters. Students should be reading chapter 8 of the course notes in order to get more information on this topic. At the conclusion of this lecture, students should be able to define a filter and name the four most common types of filters and identify the characteristics of a filter, including the gain, bandwidth, center frequency, cutoff frequency, and quality factor. The frequency response of a circuit is the analysis of the result of varying the source frequency on voltages and currents in the circuit. In prior lectures, this was examined by creating Bode diagrams. Frequency selective circuits are circuits that pass only certain signals in a desired range of frequencies to the output of a system. Examples of where these circuits are used would be in radios, telephone systems, car stereos, or televisions. Frequency selective circuits are also called filters. Filters weaken or attenuate any input signals outside of a particular frequency band. The action of a filter on an input signal results in an output signal, as shown in the following diagram. The signals passed from the input to the output fall within a band of frequencies called the passband. Frequencies not in the circuit's passband are in the stop band. The cutoff frequency separates the passband from the stop band. The cutoff frequency omega c is typically defined by engineers as the frequency for which the transfer function magnitude is decreased by 30%, or the factor 1 over the square root of 2, or negative 3 decibels. Another way of describing this is that the magnitude of h of j omega c is equal to 0.707 times the maximum value of the amplitude plot. The system bandwidth is defined as the frequency range for which the power of the output is within 1/2 of the peak output power. The frequency where the maximum average power is reduced by half is referred to as the half power frequency or the cutoff frequency. Once again, it's because P out of omega is equal to 1/2 of P out max. So if you do the math for this, this is 10 log base 10 of P out of omega is equal to 10 log base 10 1/2 of P out max, or 10 log base 10 of 1/2 plus 10 log base 10 of P max out. So 10 log base 10 of 1/2 is approximately negative 3 decibels, as we stated before. All of the filters in today's lecture will be passive filters that depend only on the passive elements, resistors, capacitors, and inductors. And because they're passive filters, their gain can only be between 0 and 1. The four major types of filters are low-pass filters, which pass low frequencies and stop high frequencies, such as a woofer; high-pass filters, which pass high frequencies and stop low frequencies, such as a tweeter; bandpass filters, which pass frequencies within a frequency band and block or attenuate frequencies outside the band, such as on a radio; and band reject or notch filters, which pass frequencies outside a frequency band and block or attenuate frequencies within the band, such as when you have unwanted noise. The following table summarizes these primary four types of filters. The first is the low pass. Notice that the gain at low frequencies for a passive filter is 1. The gain at high frequencies is 0. For high pass, at low frequencies it's 0, and at high frequencies it's 1. And for band pass, it's actually 0 at high and low frequencies, and there's a band in the middle where the gain is 1. And the band reject is 1 at high and low frequencies, and there is a frequency in the middle where it's 0. So when we're talking about band pass and band reject, that center frequency is called omega naught, or the resonant frequency. And for low pass and high pass, at the cutoff frequency, we say the magnitude is decreased by 1 over the square root of 2, as we stated before. The following plot shows a sketch of an ideal filter as well as one of the actual filter. And what you see here is that we typically model these as squares when really they die off with some type of curve based upon the Bode amplitude plot. So the low pass filter, as we stated before, has a value of 1 at low frequencies. The high pass has a value of 1 at high frequencies, and then the band pass and the band reject have 1 at either the outer frequencies or the inner frequencies. Here are some example passive circuits that would create these low pass, high pass, band pass, and band reject filters. Notice that you can use RC circuits to create a low pass and high pass filter, and you can use RLC circuits to create low pass, band pass, and band reject filters. The transfer functions for these sample circuits we provided here are low pass, h of s is equal to omega c over s plus omega c, where the cutoff frequency is 1 over RC. For the high pass, it's s over s plus omega c, where once again the cutoff is 1 over RC. For this sample bandpass filter, it's R over LS divided by S squared plus R over LS plus 1 over LC. As we have observed before, omega naught is 1 over the square root of LC, and the bandwidth is R over L. Similarly, for the band reject filter, the transfer function is S squared plus 1 over LC divided by S squared plus R over LS plus 1 over LC, and once again, omega naught is 1 over the square root of LC, and beta is the bandwidth. In order to create the magnitude plot for these, you would find the magnitude of those transfer functions for low pass, high pass, band pass, and band reject as shown here on the table. And the phase angle plots for the two first order circuits is negative arctangent of omega RC, or 90 degrees minus the arctangent of omega RC. Those last two rows represent the resonant frequency and the bandwidth for the band pass and band reject filters. The center frequency, omega naught, of a bandpass filter is defined as the frequency where the magnitude is maximum. The center frequency, omega naught, of a band reject or notch filter is defined as the frequency where the magnitude is minimum. The center frequency or resonant frequency is the frequency for which a circuit's transfer function is purely real. This was referred to as the natural frequency when we were analyzing second order circuits in the time domain. The center frequency is the geometric center of the pass band, or omega naught is equal to the square root of the low cutoff frequency times the high cutoff frequency. Notice that you only have two cutoff frequencies for band pass and band reject filters. The bandwidth beta is the width of the pass band for a pass band filter, where beta is equal to omega CT2 minus omega C1. The quality factor Q of a band pass filter is defined as the ratio of the center frequency omega naught to the bandwidth of the filter. This gives the measure of the width of the filter, and a high Q filter is greater than 1/2, or is referred to as a narrow band filter. So Q is equal to omega naught over beta. Now let's try in-class activity 1. Given the following transfer function, h of j omega is equal to 160 over 200 plus 2j omega, determine what type of filter is it, what is the cutoff frequency, what is the maximum gain, and what is the bandwidth. To determine the type of filter you have here, you analyze the circuit at two values. The first, we find the magnitude at h of j 0, and then you find the magnitude at h of j infinity. So h of j 0, we get 160 over 200, or 0.8. As omega goes to infinity, we know that we have omega in the denominator, so it goes to 0. So if I make a sketch of what this looks like, it looks like a filter that starts out at 0.8 and dies off to 0. So we know from the shape we have here that this is a low-pass filter. And we know that the maximum value is 0.1 or 0.8, so the maximum gain is 0.8. So the bandwidth is found by finding the cutoff frequency. So the way that we do that is we try to rewrite this in the form so that it looks like one of the equations we had before. So here we would have h of s is equal to 160 over 200 plus 2s, dividing numerator and denominator by 2, we get 80 over s plus 100. And if we compare this to our form for a low-pass filter, we get k omega c over s plus omega c. So omega c is equal to 100 radians per second. That would be our cutoff frequency, 100. This horizontal axis is in radians per second. And remember, that represents where the maximum gain drops by 1 over the square root of 2, or 0.707 times 0.8. Notice this is just absolute gains here. It's not decibels at this point. So we would have the cutoff frequency is 100 radians per second, and also the pass band or the bandwidth would be 100 radians per second. In class activity 2, given the following transfer function, h of s is equal to 10s over 5s plus 20, what type of filter is it? What is the cutoff frequency? What is the maximum gain? And what is the bandwidth if it's band pass or band reject filter? Or what is the pass band if it's a low pass or high pass filter? So once again, we examine the amplitude plot as omega approaches 0 and as omega approaches infinity. as omega approaches 0 and omega approaches infinity. The magnitude of h of j0 is equal to 0, and the magnitude of h of j infinity is equal to 2. So if we make a sketch of what this looks like, we have a filter that at low frequencies is 0 and at high frequencies it's 2. So this tells me that we have a high pass filter. And since the maximum value is 2, it's a high pass filter with a gain of 2. In order to find the cutoff frequency, let's compare this filter to the standard form we had. So we have 10s over 5s plus 20. Dividing by 5, we get 2s over s plus 4. And if we compare this to ks over s plus omega c, we see that the cutoff frequency omega c is equal to 4 radians per second. So if we put that value on our plot here, 4, and this is omega in radians per second, then we know at 4, that's when the maximum value is divided by the square root of 2, or 2 on the square root of 2. And once again, it has a pass band because it's a high pass filter, and the pass band would be 4 radians per second. For the system described by the following circuit, use analytical and qualitative techniques to determine the type of filter and characteristics such as the transfer function, gain, cutoff frequency, pass band, bandwidth, etc. So the first thing we want to do is to redraw the circuit in the frequency domain, and I'll have a 1 kilo ohm resistor, and the impedance of the capacitor is 1 over SC. So this is 1 over 2 micro times S. Then I have a resistor here that's 250. We measure the output across that resistor, V naught of S, and our input is VI of S. So even before we find the transfer function, which we will need eventually, we can actually analyze the circuit to determine what type of filter we have. Since S is equal to j omega, we look as the frequency goes to 0. When the frequency goes to 0, this represents DC conditions. So this circuit under DC conditions would mean that that capacitor is an open circuit. So under DC conditions, the ratio of the output to the input would be 250 over 1250. So that tells me that at low frequencies, I have a gain of 0.2. Then, as omega goes to infinity, we know that the capacitor goes to 0, which represents a short circuit. So when that looks like a short circuit, it shorts out the 1 kilo ohm resistor. So the ratio of V out over VI is equal to 1. So just by using what we have so far, we can see that we have something that at low frequencies is at 0.2, and at high frequencies it's at a 1. So we already know, based upon the analysis we've done so far, that here we have a high pass filter. In order to determine the cutoff frequency, we need to actually do the analysis and derive the transfer function. So by doing the analysis and deriving the transfer function, you get that the transfer function is S plus 500 over S plus 2500. Now, since this is not one of our standard forms for a high-pass filter, the only way to find the cutoff frequency is to actually do the analysis of h of j omega c. So the magnitude of h of j omega c is equal to 1 over the square root of 2 at the cutoff frequency. So this is equal to the square root of omega c squared plus 500 squared divided by the square root of omega c squared plus 2500 squared. So when we solve this expression, we get that the cutoff frequency is equal to 2.4 kiloradians per second. So we can now put that value on our graph. And at 2.4K, remember the horizontal axis is radians per second, we now know that the maximum value of 1 drops to 1 over the square root of 2. And once again, the pass band is the same as omega c. So the pass band is 2.4 kiloradians per second. And since it's not a bandpass or band reject filter, the bandwidth is not applicable. Let's do one final example. For the system described by the following circuit, use qualitative techniques to determine the type of filter and the gain. So once again, the qualitative techniques we're going to use is to first just analyze the circuit before we do any of the math. So we'll analyze the circuit for omega approaches 0 and omega approaches infinity. Remember, in the frequency domain, the impedance of the inductor is S 0.1 and the capacitor is 1 over S 10 micro. So as omega goes to 0, this would be DC conditions. So the inductor looks like a short circuit and the capacitor looks like an open circuit. And at that point, the output, V out over Vn, because we have that short circuit in parallel with the output, is going to be 0. As omega goes to infinity, the inductor looks like an open circuit and the capacitor looks like a short circuit. So once again, V out over Vn would be equal to 0. So this tells me that it's got to be a bandpass filter because that's the only filter we have where the extremes are 0 on both ends. And then when omega approaches omega naught, or the resonance, when you have the inductor and capacitor in parallel at resonance, that looks like an open circuit. So at that point, when it looks like an open circuit, we'll have that the ratio of V out over Vn is going to be the voltage divider 5 over 1 plus 5, or 5/6. As a side note, if we had an inductor and a capacitor in series at resonance, that looks like a short circuit. So now that we know the shape, we know that we have a bandpass filter that goes to 0, and at the resonance frequency, the maximum amplitude is 5 over 6. And remember, omega naught is equal to 1 over the square root of LC. That's our resonance value. So that's going to be equal to the resonance when we find it. So that's going to be equal to the square root of 10 micro times 100 milli. So we get that omega naught is equal to 1 kiloradian per second. Now let's try to derive the transfer function. So H of S is equal to V naught of S over VI of S, which 100 Ks over S squared plus 120 Ks plus 1 meg. So to find the cutoff frequencies, it's the magnitude of H of j omega c, which should be equal to 5 over 6 on the square root of 2, which is equal to 100 K times omega c in the numerator divided by the square root of 1 meg minus omega c squared quantity squared plus 120 K times omega c squared. So when we solve that, we get that the lower cutoff frequency is 8 radians per second. The higher cutoff frequency is 120 kiloradians per second. So the bandwidth is approximately 120 kiloradians per second. So you would put all these values on your graphs. You'd have 8 here, 120 K here, 1 K for the resonant frequency, and then show that at those two cutoff frequencies, the magnitude is approximately 5 over 6 on the square root of 2. Another way to find the resonant frequency would be to compare the transfer function to the standard form for a bandpass filter, which would look like K beta S over S squared plus beta S plus omega naught squared. And using this, you would see that omega naught squared is equal to 1 meg, or as we found before, omega naught is equal to 1 kiloradians per second. And since K is 5/6, and we see beta in the denominator is 120, we would see immediately that beta is equal to 120 kiloradians per second. And now we can use the relationship that omega C1 times omega C2 is equal to 1 meg, and omega C2 minus omega C1 is equal to 120 K to solve for the two cutoff frequencies. And this concludes today's lecture on passive filters.